Okay, a two-way slab. All right, I just want you to think of a two-way slab, questioning yourself about two-way slabs. I'm going to make it very simple for you engineers out there. Anchoring. How's it anchored? How is it anchored? It's not a two-way slab unless it's anchored in two directions. It's simple as that. I know there are formulas for you know the the span. Some of them are 2-to-1 ratio, give less than that per ACI, etc. I know that all that goes on, but remember we have also, as I said, we got the offset issue. It creates these are the columns. It creates a two-way slab differential that doesn't work. See, so I know that Professor Lehman and all the experts out there that have commented this is a two-way slab system. And I'm picking on Professor Lehman. I'm just drawing her into the conversation. We need people like Professor Lehman to reevaluate and go, oh, you know what? I reconsidered. This is not a two-way slab system. We need people of her. She has more status than Josh. Let me tell you that, right? So Josh is you can debunk him left and right. Professor Lehman, being a professor, she can always say, "Oops," and let me redirect, and it's accepted. All right, no problem. So that's why we would need Professor Lehman aboard on this, or someone of like that. Yeah, there should be some latecomers to the game. You know what? Yeah, that'd be sort of a slap in the face, but it's welcome. Latecomers again would have to be somebody who can stand up to ACI, who's not beholden to ACI, American Concrete Institute, because ultimately a lot of people get the free software and things like that from ACI, and that corrupts. That's like the free medicine from the doctors get. It corrupts them from having the ability to say what I'm saying here. ACI, I guess I get one free level of education from them, but I'm not beholden to them at all. So the offset changes the two-way slab position. All right, period. So if we can just automatically see this is no longer a two-way slab, can't we just automatically just start fighting at the pad? Stop looking for pixie dust and magical stuff. Can we get people like Professor Lehman on board? The New York Times writer, maybe, Washington Post. Maybe they can do some diving into this. And Washington Post, the guy that wrote me, maybe you can do some diving into this and see if you can debunk me on this. Now, remember, you're going to have people that, because the problem in engineering is one engineer says it's a two-way slab, and so everyone's like, I can't debunk him. And they're scared. All right, this is not I'm calling bullshit on you type of people. All right, engineers don't do that. They're more soft shoe. All right, so this is offset. It's beyond the acceptable offset. Okay, this is not therefore it's not a two-way slab. This is in the report that the engineer gives about the structure, calling it a two-way slab. And from there, everyone accepts, okay, two-way slab, let's go from there. It is not. This is not. I dare anyone I will challenge people to debunk me on that. The offsets go out of the range of ACI. So therefore, if the offset right here, goes out of ACI specs, you cannot call it a two-way slab. All right. Well, let's look in the background here, a little distribution question I asked. So I asked, here's the little fun question I asked. Distribution bars are also known as, and I'm trying to do weird questions so I can get weird answers and little different answers. What is a distribution bar is what they determine it as. The term distribution bar is sometimes used for the top reinforcement of all types of slabs. Well, it's also where they put the temperature steel. But we'll say it's distribution bar. But in accordance, it is correct, and it is correct in the case of two-way slabs, as the load is transferred in both directions. Oh, okay. So load is transferred in both directions using the steel like this, right? And the steel like this. You can pick either one as your top bar, so I don't care. Let me give a fourth one there, make it equal. Okay. So they're saying that this will equally pull. Now here's the thing about that. Deflection matters. Where will this deflect? All right, so if it's going to deflect in the center, now it can deflect somewhere else based on loading. But if we use the center there, and you look at it, you're like, okay, well, it engulfs these intersections right here, right? All right, so it's equally pressing down on this bar, this bar, this bar, and this bar. If we could think of it like that. All right, so in two directions it's pulling down. But that's not the way concrete works, is it? It depends where the steel is. If your steel is here, if your cross-section steel is there, and your top-section steel is here, you're still creating a beam effect. And it will not be quite as you may think. The bottom steel is going to take more of the load than this top steel. Now, if you mat it, put them together, lay them down together like wire mesh, all right? Now you've got a two-way deflecting steel mat. But I argue that separating these steel like this, you're just creating a beam effect. Without stirrups, you're creating just a beam without stirrups. So you have a beam, and we've already seen the way that behaves, all right? They like to fracture like that along this plane right here, breaking apart its bond with the last part of rebar, and then it comes this direction, and it's often called a shear crack, all right, shear fracture. Reality, it's losing first its bond with the bottom steel going over. In this case, the bottom steel going over may not make it back to the building, back to here. Let's call this attachment here. Heck, let's call the whole slab attached to a building all the way around. All right, the structure all the way around. Make it easy for me. No columns. So you see that if you observe this, you would say, okay, it's over here. Well, no, it's rigidity also. Remember, I state that there is a cantilever effect of the steel coming off this wall. It's more rigid. It's another zone. Okay, let's do a different color. That sucks. Let's do this. So coming off the wall, there's another critical shear zone created of rigidity. And inside that blue here is now the tributary area. And inside that, the weakest point, the most deflective weakest point is the one that reaches out the furthest. It puts its hand out the furthest. And so that would be the center here as it reaches out, okay? So it reaches out to grab from that point. Well, that's where we loaded in this case. So when you start looking for your fracture that I just talked about to one of this deflection, let's grab this color. You might see it in this zone right here, or you might see it right about here. All right, so if it was a equally distributed system as this claims it is doing, it's not doing that, you would see a fracture like that, wouldn't you? All the way around, equally distributed. You don't find those. What you'll find is a fracture that drifts towards a support. Say now these are columns, it will drift towards a support, and it may go that far and then pick up another bar and go a different direction. So it may go like this, and then the other bar may then grab that load. And on the opposite side, it may grab the load also. So this bar grabs it, and a little torque action happens, and it grabs the next bar over grabs it. So here's a bar here, and this is only 12 inches. The next, if you look at them and map it, you might find it's only 12 inches shift. You're like, oh, I see. It is to get over to that other bar. Why does it do this crazy mapping? Is that this bar grabs it to some degree, and the load is still present, and it's able to move down the line just a little bit, 12 inches, next bar. And then you see it like that, and you're like, I don't understand how it's doing that. Well, it's just like the failure in the beam. that I show you about when you have the beam there. It's first here, and then it's a little bit here, and then what's left is your concrete is left, and your steel bars up top acting as a strong back. And the load's still applying. Let's put the load there. The load's still applying, and then it might shift there towards this load. And then more load goes, and it shifts again, and then more load now hits that steel. A little different behavior, but before it hits that steel, before it hits the steel here, there is a new yeah, I was going to say critical mass, but I'm going to say there's the center of mass, the tributary area. I'm sorry, I'm going to try to switch it around for you. I won't do that. So we'll just stay with neutral axis. After this steel fails here on this side, the new neutral axis is created. The initial bump after that steel fails identifies the new profile. We got to clean that up. Identifies the new profile of the system. So once again, we have our beam effect. Here's our top steel, bottom steel. Our steel then, the loading's here. Okay. Our steel then can't hold here anymore. Via the deflection, it fractures right there, and that's that extension I talk about off the walls. That's that cantilever effect of the steel being anchored so far back. The load is there. It fractures. It's still got deflection going on. It fractures, and now the profile changes to a new. As if you remove this. It's as if you removed it, and then you're still loading this beam, and this will be a floor also. And you got the top steel and bottom steel. At that point, here's your load. They're going to match up. All right, they're going to match. All right, so you then get the initial bump of crack. If you're still loading it, what's left is this will be the new slab system design, if you will, the screening. I am going down and back up too. I'm not discounting that. The break here is pretty much fully, unless there's a little anchorage right here still. And you can count it, but this is the way the green profile of it looks like. Okay, I am counting that steel still in here. And the steel up here. So as you're loading it, this section to the right is more rigid. So this is very rigid. All that's left is this little wedge. Right, see the wedge? You can visualize that wedge now. That's all that's left. Versus what's being pushing down on it, which is the larger wedge, this area here. And you see that between the two of them here is where all the love happens. So yeah, that was brilliant. Well, that won't take long to do. Okay, loading. And let's change the color real quick. Let's put the steel in there. Let's grab some more steel here. And this top steel. Alright, so the new neutral axis is, this is already fractured. There is the fracture, and it comes up like that. And so what's left is what's left beyond the crack. So the crack is nothing holding left and right besides this new load path. And watch how this load path looks. Let's grab blue. So it looks like this. See the load path? That's it. This is already broken off. There's some where the cracked is here too. This is why I have this like that. It's gone. It's nothing there. If it can wedge itself into the wall, this can act as a shim right here and here to help also create a fracture point if it wedges in the wall. But if it's not wedged in the wall, no love, no luck. Now there is an interesting another view of this, and that is So I have my fracture here, fracture here. I now profile it a little different. Let's go, oops, wrong color. Let's go pink. So now let's do this. Let's actually map it like that. Let's be up to the steel. Let's give it that section there. Okay, so now let's change up to the bottom steel over here. What I'm driving at. So now and then let's put our top steel in and our bottom steel. And this is our loading. So now you can see that as it rotates, this section just wants to split here, right? That's so simple that you can see it. But it just wants to split apart. What's holding together is the new neutral axis, right? Wherever that may be located. This steel here. And the steel here. And obviously, the least passive least resistance is what's left. The remaining section is not fully engulfed like this. Fully still has concrete in it. So obviously the weakest point is the let's say the dimensionally thinnest point. All right, the part that's dimensionally not as thick as the rest. And it's here. But I wanted to do the second version for you to show you that, okay, look, there is a larger section. How come it doesn't turn and go that way? Well, the load is here. The force is there. It goes this way. Even though you have this large section above the steel, it's not counting. This is where the love is happening, right here. The most thin part that's left, without the thickness. So cracks matter. Depth of cracks matter. The depth of crack matters, and it will tell you what's going on. So when you're mapping this as an engineer, you should map that crack. You know, can you figure out which way direction it's going? Map your pad, map your steel, and it will start telling you, oh, okay, this is a load from here, and it's fully engulfed, and the only thing's holding these two sides together is the steel. So we've got a failed deck because once the steel spalls away or fails holding, this thing's going down. This is the short version, but I wanted to tie it into another video, but I think I might be getting a little long. So here I just wrote two-way slab. Two-way slab is a slab which is generally supported on all sides by walls or beams, and whose length to breadth ratio is less than 2. So that's that 2 scale, right? So here's 4, here's 2. So this is 2.1, then this is not a two-way slab. This is 4.999, it's not a two-way slab, all right, per ACI. Well, this one says whatever that says. And a lot of engineers don't like this this ratio. They don't look at it that way. Okay. Can you make a two-way slab that's out of proportion like this? Theoretically, I think you can. I think you can do a 5-to-2. If you understand the behavior, if you can get that metal, practice getting that metal, the mat to deflect together. If you can experiment, you can possibly say, you know what I need here? This longer length, we're going to use number 5s. And the shorter length, we're going to use number 4s. And when we put a load here, they'll equally flex, like a rubber band. They'll equally flex. So maybe we'll do 4s here, 5s in this direction, spaced at, 13 inches. You might find the ideal one. And in this direction, we have to space them at 11 inches. Theoretically, I think you can make it, go beyond this ratio thing. You just need to fine-tune your ratios. Now, this could be somebody's thesis paper, doctorates. I wish you would give me some credit for it. But this could be a doctorate on this paper alone about how to make a two-way slab using different steels and also dry running them, just the steel alone. Stop doing it with the concrete. You don't need the concrete on here to check the behavior of two-way slab systems. You can just simply lay the steel down, load it. If they look like they're not stressing the same, well, then they're not a two-way slab. If they're not behaving the same, one stretching longer than the other, they're not a two-way slab. Okay, so there you go. There's a doctorate's paper for somebody. But don't forget to give me my credit. Yeah, I just turned the recording on because, not to look at this for you guys, but if you want to, Shadow just gave a shout out, so I wanted to see if we can catch her again. If we can catch her giving another shout out. Alright, so anybody follow me on my machine, the lift, I spoke to the engineer that manufactures it. We're both on the same page. I will give him credit that I was looking for bypass, and I showed him my 2 valves for bypass, and with his experience, he said, try using the hand pump, and as he said it, I quickly knew where he was going with it, and I was like, oh, so simple. So shout out to that. That's in another video. I guess, again, this was just for Shadow in the background, but now we don't get to hear Shadow, so let me get back to the content. Shadow's my cat, for anybody you guys know. 2 years ago, broke me down. I cried. I got it from a stray. I pick up strays. I don't throw away cats. You got a cat, I'll try to find it. I won't try to find its home. It want to be being my home, but I'll try to find it into my home if I can. I got 2 cats outside. Come on, Shadow. You're not kicking in the background. 2 cats outside. As of last night, I got another little teeny one came up to eat. Oh, I feed my babies. I do not believe... I'm one of the ones who will feed someone. I feed bums on the street, guys. If I see them going through the trash can, oh no, oh no. I stop what I'm doing. I go to the store, come back, track them down, and give them food. All right, bye. I'm going to try one more thing. Hold on. All right, maybe I'll end it with this. So I have a series of videos going to come up. It's going to deal with overpressure. Overpressure is going to explain everything from how you can hear my voice, how I'm vibrating the air that you can hear my voice. I'm trickily... Uh-oh, I think that was her. I'm being tricky when I talk about 19% and 16%. I already gave it to Embry on the 16% because I didn't put the video out yet, or maybe I did on the other channel on Rumble, but Embry said something, and I'm waiting for somebody to try to debunk me on the 16%. And I don't know if I posted it yet, but there's a couple of rules. 21% oxygen is in the air. 19.5 is what OSHA says you need. And I have a 16%. Well, I said for life. And for fire to survive, it needs, well, they state 16%. And then it starts smoking, it starts burning itself out. If it can't maintain at least 16%. So I just want to tell you what I got coming up. I want to really teach you about overpressure, why it's so important in your whole life, why it will help you explain your car moving down your road, you throwing a baseball, a bullet, what happens with a bullet, what happens with an explosion. You'll be able now to look at all this stuff that's going on, this drama of all these explosions when they show you a crater site. And you'll be able to tell me what took place based on overpressure. You'll be able to tell me the force it would have taken, roughly, what explosive pressure it would have taken to cause whatever damage you're looking at. You'll be able to tell me how the building gets taken out by a car that parks in front of it and takes out the whole front of a building when it does that. You'll be able to also, with that, know how to duck overpressure if it was to come at you. One of the things you're going to do, some people tell you to open your mouth, right? To try to do that ballooning thing. Yeah, I'm not into that one. If anything, I would tell you guys, if you knew it was going to happen, you would exhale real quickly, cover your eyes. The things that can't take overpressure, plug your ears, cover your eyes, which you got to be careful with negative pressure too. But I would tell you to blow out, not to open your mouth, as some myth says. So I'll give you a little hint. For example, you could look at snap telephone poles, and it's been determined that only 5 pounds of overpressure snaps telephone poles. Of course, it depends on the pole and the anchorage, the tie wires, anchor wires that are holding it down. So that may not be the greatest one to look at. Okay, so this one says steel frame just distribute it and pull away from the foundation. Well, this is also not true. It depends on the anchorage to get this 3 pounds of overpressure. Remember overpressure, and we're going to go deeply into this. I'm going to just give you this 6959 at sea level. So they're stating when you get to 3 plus 3, all right, that's overpressure. You're at 1769. This will destroy buildings. No, not no. You still need the just because you have overpressure, you still need the pole or whatever to be able to move the hell out of the way. For example, that pole, a steel building, braced correctly, 3 pounds of overpressure won't do a damn thing to it. All right, so it may be experiencing 3 pounds of overpressure, but if it's just too general a question. You need to know the shape of the building. Does it have a lot of windows? 3 pounds overpressure, you're going to break the windows. The pressure is going to be now equalized inside real quickly. And now it's going to be a balance on the other side. So here, let's just use a steel frame. 3 pounds coming this way, 18 pounds coming this way. On this side, you got 15 pounds, all right? It breaks a window. It comes in there. It starts flooding that compartment. The 18 pounds reaches 15 pounds. It starts building up pressure inside there. It changes 15 to 16 real quickly. Now it's 16 versus 18. The pressure still comes in. 17 versus 18. This takes down the pressure outside because this is now going into this compartment. And when you get to 18 and 18 on each side, there is no overpressure. This stays right where it is. It's overpressure of atmospheric pressure still, but there is no overpressure on this steel. All right, there is no PSI pressing on that steel. It's just compressing. It's just compressing equally both sides. No harm, no foul. So this is, I'm going to teach you how to, I'm going to teach you this stuff and you're going to put it together. All right, this is ending the video, and this is just a teaser for, I'm going to teach you about overpressure and how important it is. Lastly, I'll state that I can't talk to you without overpressure. That means my lungs are creating more pressure than the atmospheric pressure around it to be able to talk to you. I'm vibrating the air, and the vibration of the air to you sounds like these words. I've magically synchronized the air frequency to where you do it also. We make each other hear the same word, no. Some people who speak foreign language vibrate the air a little differently when they say the word no, and it's kind of irritating because we have a conclusive file. We have a range of how we accept the word no or waffle. Some people don't like the way people say waffle. Waffle. I'm trying to do it and purposely mess it up a bit where you're like, no, man, it's waffle. Waffle, waffle, waffle. It's like a WA thing. The waffle, woeful. Anyway, you get my point, is that the person's not vibrating the air like we're used to hearing it, so we get irritated. That's the amygdala. It's petty bitch. I told you about the amygdala. So, you have to understand, they just have to learn how to vibrate the frequency of the air differently. So if I want to raise my voice, I have to use more air, overpressure, to get the voice to travel longer. I'm going to do it now. Hold on. Oh! So I just did an overpressure out of my lungs that made that vibration go even longer, further away. Overpressure was a sound wave that went out as far as you can hear it. And as a person can only hear it, it may be loud right to you, but no one else heard it, 40 feet away. So the overpressure fades off before it's equaled and stopped. This is why you can hear a police car siren. It's called overshooting your siren. Basically, you're going 90 miles an hour. You got your siren on. The people can't hear the siren until the car's practically on them. And that's because he's going faster than the overpressure of the vibration of the siren. And they call it overshooting it, but in reality, it's overpressure. He's going faster than the overpressure created by the siren. He could not overshoot it if they could turn the siren up louder. The loud truck horns, they have an overpressure that is so loud, and that's where you hear the honk compared to your little beep beep car. Creates a small little vibration. End of video. Love you guys. But go back to the beginning of this video, and then this was a teaser to overpressure. Bye.